So thank you very much for the introduction. I would like also to thank the organizers and the program committee to invite me to give this progress report. This will be a progress report on work that we started in Zurich about 12 years ago, which aims at controlling the translational motion of atoms and molecules in Rydberg states. And we call these Rydberg atoms and molecules. So I will begin with a short general introduction. Then in the second part, I will explain how we manipulate the translational motion of these atoms and molecules. And in the end, I will present three applications, one in which we have, after trapping, looked in detail on how the atoms or molecules that we trap leave the trap, which are the processes that causes this trap loss. Then I will present briefly two new type of results in which we try to repeat these measurements with electrodes that we place on a chip. Last application is using this methodology to study ion molecule reaction at very low energies. These last two topics, mostly the last one, I haven't published yet, so this is the first publication, and this is also the reason why two authors that are not on the abstract, Piet Allmendinger and Johannes Deigelmeier, are now authors, although they are not authors in the abstract book. So I'll start now with the introduction. So general introduction on the manipulation of atoms and molecules with electric field and magnetic field. Nowadays, when one has atoms with closed optical cycle, the best way to manipulate the translational motion is with laser radiation. And we heard about this earlier this week, or last week. However, one can, for molecules that do not have closed cycle, use inhomogeneous magnetic and electric fields to try to generate cold samples of atoms and molecules and to manipulate the translational motion of these atoms and molecules. And this is what I will tell you about, and one can trace the origin of that field to the experiment of Stern and Gerlach, which use an inhomogeneous magnetic field to separate a beam of argon atom into the magnetic components. So the principle is that a system, a paramagnetic atom, which has a magnetic dipole moment, has a Zeeman energy, which is given by this expression. And now the gradient of the energy is a force, and one can express the force if the magnetic moment doesn't depend too strongly on the magnetic field, and it's proportional to the gradient of the magnetic field. So this is well known, and it has been successfully used by Stern and Gerlach. Similar experiment, but using inhomogeneous electric fields, have been conducted in the mid-50s of last century, and they were used to generate the first maser. And it was ammonia molecule that were used in this article, and they passed through the inhomogeneous field generated by 4 rods in quadrupole configuration. And in this configuration, one has on axis a region of low electric field, and the levels of ammonia, which have an energy that increases with the field, are attracted by the region of low field on axis, and this is a way, and those that are in this lower component are repelled, and this is a way to actually focus a beam on axis and eliminate this component, and then one achieves population inversion. So these methods now are used more and more by chemists and physicists who want to look at the properties of cold atoms and molecules. And there are 3 methods related to these, and that are actually started with some work of Gerhard Meyer at the Fritz Haber Institute, and actually this work was still when he was in Holland, in which he uses a supersonic expansion to cool molecules in the expansion to the ground rotational vibrational state, and then decelerate the fast supersonic beam using pairs of electrodes, many pairs of these electrodes, and generate inhomogeneous field, and sequentially take some energy off the beam until the beam at the end runs out of kinetic energy and can be trapped. So these methods have then been extended to paramagnetic species, and one uses then inhomogeneous magnetic field in the same configuration and exactly the same principles. One has deceleration stages, which are now coils, through which one applies currents to generate inhomogeneous magnetic field, and one decelerates the beam along its axis until at the end the beam has run out of kinetic energy and can be trapped. Now, these two methods, they are used, this is used for polar molecules, can be used for any paramagnetic atom or molecules, but sometimes the molecules do not cooperate. Like if you take H2 or methane or nitrogen in their ground state, they are neither paramagnetic nor dipolar. So if one wants to do experiment with these, and in my group, we particularly like H2, one needs to do something different. And what is different is what is the subject of this talk. And what is different is that we first generate the dipole in these molecules by exciting them to Rydberg states and then decelerate. So this is what I've had. This is now our decelerator. Our decelerator will be similar to this one, but it will have only one stage. We don't need 100 stages, but just one. And the reason why this is so is that we generate the dipole, electric dipole, that we want in the system. And if we go to an n equal 30 Rydberg state, we can easily have an electric dipole moment of 3,000 dBi. So the force will be 3,000 times stronger, so we can use a factor of 3,000 less deceleration stages for the experiment. And this is what I will tell you. So we can decelerate atoms, H2, or non-polar molecule. So now, a quick reminder, there was this morning a session of Rydberg states, and here I am again with this in a different session, but I have to say a few words about this. So what we exploit is the fact that all atoms and all molecules have Rydberg states. In hydrogen atom, there's only one series because there's a high degree of degeneracy. In the alkali metal atoms, one has the penetrating state that have a non-zero quantum defect and the penetrating levels. And in molecules, we also have these states. However, we have this series of penetrating and non-penetrating states that converge on every quantum state of an ion. So there are many more series in the molecules, but they are there, and one can exploit them. They have similar physical properties than its atoms, and one can use them in the same way. So I will be telling mostly about hydrogen atom and hydrogen molecule. So I should say the best definition of a Rydberg state is a Rydberg state, the spectral position of which is given by Rydberg formula that everyone knows. So now, a similar transparency has been shown by Rosario this morning that shows how the physical properties of Rydberg atoms and Rydberg molecules scale with the principal quantum number. So the radius, it grows with n squared. The binding energy decreases with 1 over n squared. The fields that one needs to ionize this system decreases very rapidly as 1 over n4. The radiative lifetime, I have not put a scaling because it depends whether one has electric fields or, but in general, it's at least, it increases at least with n cubed. And what will be important here is the induced dipole moment, the dipole moment you induce in this system with an electric field, and that scales as n squared. And this is what I told you before. If you go beyond n equal 25, the dipole moment is already very large. There are further properties that scales rapidly with n. Now, what I will tell you about is actually from the point of view of ideas, not new. It was proposed already in the early 1980s. In the early 1980s, there were two proposals, not experiments, but proposals, to actually use the electric dipole moment of atoms to trap them. And the goal of trapping, one wanted to trap to make precision spectroscopy, atomic clocks, and trapping these systems. So I like to read these sentences because they illustrate how often things are ripe from a theoretical point of view many years before they are ripe experimentally. So here it says, Rydberg atoms exhibit large electric dipole moments, suggesting that inhomogeneous field can exert its forces on them. The resultant change in kinetic energy is equal to the Stark shift of the Rydberg. We will see that soon. So in the same, just 1 year before, there was a proposal even on how to make a trap for these atoms by William Wing. It says at moderate field strength, Rydberg atoms have trap depth comparable to ambient KT and as much as 100 times those of recently proposed optical field traps. So, of course, for atoms, one found soon after this that it was a better way to laser cool. But for molecules, these are still very attractive methods because laser cooling is not always an option. So now, very quickly, the principle. So this is what I've given here is an energy diagram, and here you have an electric field scale, and I show here the energy of the hydrogen atom in the field. And what you see is for n equal 8, 9, 10, that the energy levels split. They are degenerate at zero field, so there's a linear Stark effect, and some states go up in energy, some states go down in energy, and these are called low field seeking state, and those are called high field seeking states. So now if we want to go through the number of what we may expect in an experiment, this is indicated here. So we have an induced dipole moment. It's 1.5 electric charge, Bohr radius, n squared. So as I said, several thousand dpi. The Stark energy will be given by this expression, and the force, if we have a gradient, will be equal to the electric dipole moment multiplied by the gradient of the field. So now if we take values, hydrogen atom, n equal 30, a gradient of 3 kilovolts per square centimeter can easily be done in a laboratory environment. If you put this number, you come to an acceleration of 2 times 10 to the 8 meter per square second, which is absolutely enormous. This is the reason why we can have very compact decelerator and have that I showed before. Now, we were not the first to exploit these properties in an experiment. The first one was Tim Softley and his co-workers at Oxford, and they used a dipole rod, so 2 wires with opposite electric potential to generate an inhomogeneous field. The field would be large, close to these 2 rods, and when you move away, will become smaller and smaller. And what they did, they generated the Stark effect in atoms of krypton, and here you see for n equal 18 Stark states. So here you have the low field seeking state, here the high field seeking state. And you expect that the low field seeking state here will seek the region far away from the rods, while the other ones will seek the region of the rods. And what they did, they had an imaging MCP here, and they monitored the deflection of the beam after preparing these components spectroscopically. And you see the low field seeking state, which is this one, is deviated upwards, and the high field seeking is deviated downward. So that verifies the principle. Now what I will tell you is how we used the same principle, but now to decelerate a supersonic beam. And I will start with experiments we did on hydrogen atom. We started, in fact, doing experiment on argon, but I'll show the experiment on hydrogen atoms here because they are pedagogically easier to follow. So we have we have a mixture. We start with a mixture of argon and ammonia. And we are chemists, so we generate hydrogen atom through a photodissociation reaction. We dissociate ammonia by focusing an excimer laser in a capillary at the exit of this nozzle. Here we generate H atoms, and there is a supersonic expansion here, and the H atom will move through the system with a velocity of typically 700 meters per second. Now, I'm using the units that spectroscopists use is the centimeter to the -1. So the kinetic energy of hydrogen atom at 700 meters per second is 20.5 centimeter to the -1. So this is the energy we would want to typically remove to stop the atoms. So in the first experiment, we had a very simple system. We had 2 electrodes with a wedge. Here there is homogeneous field. We use this region to prepare a well-defined Stark state, and then we let the system move from a high field region to a low field region. This is the first experiment. Well, the first experiment we did, we actually wanted to illustrate the procedure, and we excited in this energy versus field map at a position where we had 2 Stark states crossing exactly. One being the bluest state, of the n equal 22 manifold, and one being in the middle of the n equal 23 manifold. So we excited in the high field region, let the atom fly out of the field, and then we measured their time of flight. So short time of flight means a fast atom, and a long time of flight means a slow atom. So first, we don't apply any field, and we calibrate the velocity distribution of our beam. Then we turn the field on to decelerate, and then we see 2 peaks. One of them corresponds to these n equal 23 states. They are hardly changed because there is no Stark shift. And this one is actually accelerated, and the difference in energy is what we have gained in kinetic energy. And here are the results up there. So we have a Stark shift at n equal 22 of 18.5 centimeter to the -1 when we apply 600 volts per centimeter. The initial velocity is 700 meters per second. The translational temperature that we calibrate in a different experiment is 1 Kelvin. And so what we managed to do here is to add 18 centimeters to the -1 by letting these atoms fly out of the field. So we have doubled their kinetic energy from here to here. So if we can double the kinetic energy, that means that we can also take it out. And that's what I'll show now. So in order to decelerate and trap, we modify the system a little bit, because we want, after deceleration, to load the trap. And we do this adiabatically. So we start with now 4 electrodes in a quadrupolar configuration. Here of -1000 volt, 1000 volt, -45, +45. That generates this field distribution. And here we excite. The atoms in the supersonic beam move in this direction, and they will feel a growing field in this direction. So we will slow down the low field-seeking atoms. However, if we now let this configuration stable, the atoms would move up the field until they ionize. This is not what we want. So as the time goes and the atoms move forward, we reduce the electric potential on these two electrodes so that we keep decelerating the atoms at almost constant field. And then if we do the experiment well, we can pre-calculate the sequence. We can make sure that these potentials have relaxed into a quadrupole trap at the end of the deceleration. And if we do things right, the atoms are in the middle of the trap. Once we want to detect what is in the trap, we actually reverse the electric potential. We put a high potential on these two electrodes, 0 here, and that will extract the ion. And we can read out what is in the trap. So this is what is shown here. So here we take images of the cloud in our trap after 35 microseconds all the way to 100 microseconds, and we see how the atoms we have loaded in the trap breathe. And we can completely simulate this. These are simulated images because we know what we are doing. We know the field we apply, we know the dipole moment of the state we have prepared. And now, this is what has happened. So we have stopped the atoms. We had 700 meters per second in 1.8 millimeter and in 5 microseconds, and effectively we could achieve this acceleration, or this is a minus sign, it's a deceleration. So this is a way, general way, to actually have a supersonic beam of atoms and molecules, stop them, and load it into a trap. Now comes something that intrigues us at this time. Once you are in the trap, you can do a first scientific measurement. You say, well, how quickly will the atoms leave the trap? So you make a control measurement where you don't trap, and you see the atoms just pass through, and then you trap, and these are the dotted lines. And you see that we lose the atoms quite rapidly, up to about 120 microseconds, and afterwards we have almost an exponential decay with a decay constant tau of 135 microseconds. Now, you remember at the beginning, I told you the lifetime increased at least with n cube. What we did, we measured at n equals 30, at 25, and we never saw any difference in the lifetime we measured. So we were highly surprised. We thought the lifetime would increase as we increase, and this was not the case. I will have to come back to this later. Now, we wanted to show that we can also do that with molecules. These are here the similar measurement in hydrogen molecule now at n equals 30. And to demonstrate trapping, what we do, we take a spectrum of hydrogen. In order to have long-lived state in hydrogen, we use circularly polarized light to prepare M equals 3 level, which do not have sp and d component. These are the predissociative state in H2. So they are long-lived. Here, we take the Stark spectrum. You can count the Stark effect. They are equivalent to this n equals 22. And then we can afterwards load the trap and look at what is in our trap, and we see that we only trap the states that have a large dipole moment of the right sign. And these are. And then we do this. Here the atoms remained 50 microseconds in the trap. What we find here is that the trapping time now, they are different from a hydrogen atom. They are 35 microseconds. We had a density of 10 to the 6 to 10 to the 7 atoms per cubic centimeter, and we had a temperature of 150 millikelvin that we measure by the normal methods. So here again, we did not see much effect of n, although I told you the lifetime should increase with n cube. So now I come to the application part where I will try to explain to you what we have done since to try to understand how the atoms leave a trap. So this is the first time one can do that, load Rydberg atom in a trap and observe them until they are not there anymore. So what can one expect? So I have here written possible processes that can happen in the trap. The Rydberg state are excited states. They can actually spontaneously emit and go down to a lower state. Or in a molecule, they could predissociate. They could undergo collisions with other atoms and molecules either in the trap or in the trailing part of the beam. Or they could undergo transition induced by blackbody radiation. Now, how do we distinguish this experimentally? We can actually, this point we can distinguish. We can actually, while decelerated, deflect the atoms so that they are no longer in the beam. And here we can actually try to cool the chamber so that we have less blackbody radiation. And I will show you the results from these two types of measurement. The first type of measurement is when we deflect the beam. So how are we going to do this? We build a new decelerator, which consists of our original decelerator, and we put an identical one here with two traps. So we can either trap them here, and detect them at this point in our detector, or we can deflect them while we decelerate, store them here, and monitor them there. And then here, once we are here, we can look at how the magnitude of this signal varies with time here and here. And this is represented here. In blue is off-axis, and in black is on-axis. So here you see very well that we can see that this early part comes from atoms in the beam that knock the atom we have trapped as they pass along. A typical supersonic beam is 100 microsecond long, so you can see very well that the other atoms in a beam are actually depleting our trap. So now we know, so it's better to do the measurement when we trap off-axis, where we don't have this loss. But the asymptotic, or the lifetime remains this 135 microsecond, and is still n independent. Now, in order to see something else than this, we had to cool the machine. We had to first cool it to liquid nitrogen temperature and then to 11 Kelvin. And now what I show you is for hydrogen atom at n equal 30, a measurement at room temperature where we have this exponential decay with a time of 135 microsecond. And then in black and blue are experiments that we have done by cooling the region of our trap to 125 Kelvin and 11 Kelvin respectively. And now suddenly we start seeing, of course, a signal much longer, and we see that the decay is actually not exponential, but non-exponential. So it appears that the decay depends on the temperature of your apparatus. And here, at 11 Kelvin, we could actually start seeing behavior specific of the Rydberg state we prepared. So what I show here is our decay, the trap decay measurement between 0 and 3 milliseconds at n equal 27, 29, 31, 33, and the even numbers are here. So we see that we trap now longer at these lower temperatures if we increase n. But the decay is still non-exponential. So how do we understand what is happening? So the processes, they are radiative processes, and I have to say something about the radiative processes. So one of the important radiative processes is actually the emission, spontaneous emission, and the strongest of this process is the emission to the lowest possible state, because the Einstein A coefficient varies rapidly with the frequency. The other processes are the processes indicated in red, and they are induced by the blackbody radiation. So one process is the ionization by the blackbody radiation. So we lose then the particles in the trap because they are ionized, or they are transitions to neighboring states. When that happens, we don't automatically lose the atoms for the trap because low frequency transitions do not usually change the dipole match. It needs many of them. So we can then, by the rates of these processes in hydrogen are well known, one can calculate them, and then one can generate a computer program which will calculate the Monte Carlo program, which will reconstruct the decay. So this is what I will show next. And so these are the measurement I showed you before, these dots, and this is what we calculate when we include all the processes that we know, all the radiative processes, ionization, stimulated emission. And actually, the calculation do extremely poorly in describing what we see. Actually, they do well at the beginning, and they have the right slope at the end, but here they don't do well at all. And actually, we predict in the trap almost 2 orders of magnitude less atoms than we have. So there are other processes that are taking place. And these processes, actually, they come relatively early on when we have high density of Rydberg atoms, and we can show now by simulation that they come from dipole-dipole interaction between the Rydberg atoms in the trap. This is work that we do in collaboration with Pierre Pillet in Orsay. Now, we, of course, can compare atoms and molecules in our cold environment, 11 Kelvin, and we see that now hydrogen molecule, they live much longer than H atom in the trap, 280 microsecond. The main reason why this is so is that when you prepare m equal 3, the highest frequency radiative process goes to n equal 2, while here it goes to n equal 1. So we understand this qualitatively. Now, I come to, I have only 45 seconds. So I jump now to the end, where I will show you some measurement of the reaction, H2 plus H2. And I'm going to show you with the methods that we do. That's 5 minutes discussion, or Yeah, so I will use 1 minute of the discussion. So we use H2 plus H2 to generate H3 plus H. This is a fundamental reaction of astrophysics. And there have been no measurement of this reaction at the conditions in the interstellar medium, that is around 10 Kelvin. So what we are doing now, we are using our ability to control the velocity of H2 Rydberg state to look at this reaction H2 plus H2. So we look at the reaction within the Rydberg orbit. So we prepare H2 in a large Rydberg state, we let it collide with H2, and then we generate H3 in a Rydberg state and detect it. So the electron will be a spectator in this reaction. So the experiment is the following. We have a beam of H2 Rydberg state, which we deflect with using a surface decelerator and deflector, and we merge it with a beam of H2, and we can control the velocity of each beam extremely precisely. And then we tune the velocity, or we tune the velocity difference, and therefore we have the collision energy. So for instance, if we choose 2,400 meters per second for the H2 beam, and 1,600 meters per second for the Rydberg beam, we have 6 milli-electron-volt collision energy. If we choose more similar velocities, we can go down to collision energy of 0.1 milli-electron-volt. So maybe, just to give you an idea, when you do the measurement, we can actually detect in each shot H3+. It's a very sensitive measurement, because the beams are dense. Now I'll show you the result. So this is the H2 plus H2 reaction had been studied at above 6 milli-electron-volt by Gerlich and Glene-Winkelmeyer. These are the black dots. This is the lower collision energy that had been studied so far. And what we have done, we have done a measurement here so that we can calibrate our cross-section to theirs, because we only measure relative cross-section. And then we have bridged the gap all the way down to 10 millikelvin. And you see, what I've given is a dashed line, which gives what one expects from a Langevin capture cross-section. So we see a small deviation as we approach low energies. If you want to learn more about this, there's a poster by Piet Almendinger, poster 48, and this is my group. So I want to mention Piet Almendinger, Christian Seiler, Johannes Daigelmeier, and Pierre Pillet. And these are the technicians who helped us in these measurements. I thank you for your attention.